What's up everyone, and welcome to my tutorial in pragmatic data science. So in the previous video we calculated the documents and the term frequency and the TF-IDF for all of the words that occurs in all of the songs. So the next thing we're gonna do is we're gonna have a look at here in the README. So the next thing we're gonna do is we're gonna do some sampling. And the reason why we do this, I'm gonna jump a little bit ahead of times here, because later we're gonna do similarity. And if you imagine that we're gonna do similarity between documents, let's say that we have 5 documents. So we have document 1, 2, 3, 4, 5, and then also we have similarities between each of these documents. What's going to happen is basically that you're going to have something that is called Cartesian product, which is, very not nice when it comes to complexity. So let me just show you something here real quick. So if we want to calculate the similarities here for each row, if you think of this like a matrix, like similarity between each row and column here, maybe we have 20% here, and I don't know like how many percentage it is basically. But what's gonna happen here is that we gonna have a complexity that grows very quickly. So for example, if we, and in this example I say that n is equal to 5, but if n is equal to 6, it's going to create another 6 here and then another 6 here. And now what we have gained is all of these indexes here. I can't even do it here properly, but like all the way out here, and also for the whole column here. So basically it doesn't scale particularly nice. It's called the Cartesian product, and in terms of time complexity is n squared. So that basically doesn't hold for larger data sets. So if we have 55,000, it's going to be 55,000 times 55,000. And that's a huge number, and we can't really calculate that. So instead what we're going to do is you can solve this in different ways. And in this particular video, I'm going to do sampling of data. Because the problem that we are trying to solve here, we don't need to use each document, and figure out what the difference is and so on. Sometimes you need that, and then you have to do other stuff like min hashing, or I don't know, there's some other algorithms you can use also. But what we're gonna do here instead is we're gonna take the data, and then we're gonna grab some subset of the data, and we're gonna keep all the statistical significance within the sample. And then we're going to use that smaller set of data instead, because then we can control how big the data is. So that's what sampling is. So we're gonna see here what this sample.py does. And you can see it's very similar to the previous stuff that I showed you from the main.py file. It also has this like pickle thingy. And then I'm going to do, by the way, you can sample in many ways. I'm going to do it with reservoir sampling. And you can see here also that I've calculated my documents here, and the document frequency, they're over like bin files. So I'm just going to load them, and you can check out the previous video how we calculated these with TF-IDF. And then what I'm going to do is I'm going to set K to 1000. And what this means is basically that regardless of how many data items I have in my bigger documents dataset here that I loaded, I'm going to sample it down to 1000 examples. And then I'm also going to pickle that into something called sample.bin, and then I'm going to print some stuff. So let's have a look at this. It's a really simple algorithm that is very, very straightforward and easy. And let's have a look at what it does. So I take here's like the whole data set here. And here is the list of documents that I will be my sampling. So the first thing that I do is I take these documents and I shuffle them randomly. And I do this because I want it to not sample it exactly the same every time I run it. So, and then I'm gonna eventually fill up this reservoir until 1,000 items, and I'm gonna return it. So what I do here is basically say that while I don't, at first, it's empty. So I need to fill it up with 1,000 items when k is equal to 1,000. So before I do anything else, I just fill it up basically. So it's filled up into k items here from the documents. And then the next thing I do is I continue here from k where I left off, and then I grab, and remember, I have the I number here, which is increasing by 1 on each iteration. So the next thing I do is I generate a random number between 0 and I minus 1, and then I get j here. So if j is less than k, I sample it into the j index from the document I. So, I mean, this is a bit mind-boggling. But I think the first part here is pretty straightforward. I fill it up with the first k items, and after that, I create a random number, and it's getting increasingly more rare that j is going to be less than k, right? Because what I do here is I create a bigger and bigger interval in which I create random numbers from, and it's linearly scaling up to the length of all the documents, right? So there's going to be less and less sampling going on. It's going to be sampling really hard here in the beginning, and then it's going to be less and less frequent. That it's going to be basically I over n probability that a swapping will take place, and the actual documents that is going to swap is document I. So this is a really hard part to understand, but it's really not that complicated, right? So take a while and figure out what this means, basically. So it's going to be doing a lot of samplings in the beginning, but then it's going to be less and less frequent that it's going to swap out the document, and it's going to swap out one at random. So the index here is random. All right, so that's what it does. So let's go ahead and run that and let's see what it does. It's actually kind of quick, so it should be, I think it should be pretty fast. All right, yeah, so it's done. There was actually 55,650 songs in this dataset, but now I've sampled it down to 1,000 random samples with the reservoir sampling uniformly at random. So I think also it's probably also here. I think I also followed the Wikipedia. I think I followed the Wikipedia article here when I implemented this, because I also not remember it. So the thing you have to consider here, if you're following along with the Wikipedia stuff, and mathematical notation is always gonna start from 1, right? So you're gonna have index out of bounds exceptions like crazy here if you don't think this through. And my general advice here is that if you're implementing stuff like this, of course you shouldn't implementing it like I do in a production environment most of the time, because then you would use reservoir sampling from libraries like scikit-learn or anything like that. But for an understanding of what it does and the mechanisms of it, I think you should always implement it first. But if you follow along with mathematical annotations like this, they're going to be doing indexes from 1 almost all the time. So what's going to happen here is you're going to have an index out of bounds somewhere here, I think. So basically what you do instead of counting by 1, from 1, you start counting from 0. But that also means that you have to change stuff like this. So while it's equal to k instead of k plus 1, and then it's going to be sampling from 0 to I minus 1 here, and then you're going to also remove the equal sign here, so it's going to be strictly less than k. So I think that through. Inclusive range. So that is basically all for this video, and you can see also that it dumped this variable here called sample.bin that we're going to use in the next video. So I suggest you go ahead and try this out. And of course, you can implement other sampling algorithms. I think reservoir sampling is the most common one. And as I said in the previous video, I'm going to go through the most common algorithms because that's going to be the most useful thing for you. All right, so I hope you guys liked it, and don't forget to subscribe, and I will see you in the next video. Bye-bye.